Hi students, my name is Dr. Marie Wong, and what I want to do is talk to you today about how to do hand calculations and also show you some SPSS output for one-way ANOVA. So when we do one-way ANOVA, we typically have 3 sample means. We can have more, but it's typically, in my example here, we have 3 sample means. And the way I've set this up is we have an independent variable, which is music type. So people either listen to pop, rap, or country music, and the dependent variable is their mood. So with you, I have some preliminary information here for us to use when we do our calculations. So for the pop music condition, T refers to a summary. It's like a sigma X within a condition. So with the pop condition, T is simply all the scores in that condition added up. That's what T1 is, 29. If we added up all the scores in the pop condition, we would get 29. If we added up all the scores in the rap condition, that's T2, we'd get 13. If we added up all the scores in the country music condition, that's T3, we would get 10. So T in this case for one-way ANOVA is simply the same thing as sigma X within a condition. For sum of squares, that's provided for you. So for the pop condition, it's 5.87. For rap, it's 1.88. And for country, it's 1.50. I have 8 participants in each condition, so N is 8 across the board for each participant. And then finally, I have a mean of 3.625 for pop, a mean of 1.625 for rap, and a mean of 1.25 for country. So the mean is just the average level of mood that people reported, and higher numbers are representing a better mood. Okay, so there was a mood scale, and people, when they listened to the music, after they listened to it, they rated their mood. And again, it was set up so higher numbers represent a better mood, lower numbers represent a worse mood. Then finally, in the small box on the right, K is 3. Remember, K is the number of conditions that we have. G is 52. So G is if we added up all the scores across each condition, right? So remember the T's, that was the sum within a condition of all the scores. So if I want to add up the scores across my entire study, I can just add my T's together. So you can get G, that G of 52, by taking 29, which is T1, plus 13, which is T2, plus 10, which is T3, and you'll get 52. Or you can just take all the 24 scores that you're working with across your data set and add them up, and you would get 52. Big N is 24. It includes across all conditions the number of participants we have. And then sigma X squared, that's if we took every score in our data set and squared it and then added those squared scores up. So that's 148. So we need all of this to do our hand calculations in ANOVA. So we're sort of starting in the middle a little bit. Otherwise, the problem gets too long to calculate by hand. So what we're going to do now, I'm going to show you how to calculate sum of squares within, sum of squares between, and sum of squares total for a one-way ANOVA. And we're also going to put this into a source table. But before I get to that, I want to talk to you again about hypotheses and critical value and also degrees of freedom. So we have to get that out of the way before we do the hand calculations. Okay, so hypotheses. In a one-way ANOVA, it's just mu1 equals mu2 equals mu3. We're essentially saying there's no difference across conditions. The kind of music played shouldn't matter. It shouldn't be affecting people's moods. We're going to get the same mean in mood regardless of the music being played. The research hypothesis is at least one of the means differs from the others. Now we would look up, to get the critical value for ANOVA, you would look up in an F table, a table of critical F values. And again, you can find these in the back of stats books, these tables, or you also can look online. You can Google it and look up critical values in the F table, and you should find what you need there. We're setting alpha at 0.05. That's just a convention we use in psychology. Our degrees of freedom to look this up are 2 and 21. So in the F table, it asks you for degrees of freedom for the numerator and the denominator of your F statistic. The numerator is degrees of freedom between. The denominator is degrees of freedom within. And if you look to the far right of the screen, you'll see that I calculated degrees of freedom for you. I'm going to get back to that in just a second. But for now, we have degrees of freedom 2 for the numerator, 21 for the denominator. We're going to go look that up in the F table along with our alpha level. The critical value we're going to end up with when we look that up is 3.47. All right, so now what we have are degrees of freedom total. The way we calculate that is just big N minus 1. So big N, that's everybody in our research study. That's our total N, our total sample size, which was 24. So 24 minus 1 is 23. Our degrees of freedom between, that's the numerator. Degrees of freedom numerator or between is K minus 1. K is just the number of conditions we have or the number of groups that we have. So that's going to be 3. K was 3, so 3 minus 1 is 2. That's our degrees of freedom for the numerator of the F statistic. And then the degrees of freedom for the denominator is our degrees of freedom within, which is big N minus K. Big N is 24. K is 3, so 24 minus 3 is 21. So these are the degrees of freedom we're going to be working with. We need them. We need degrees of freedom between and degrees of freedom within to look up our critical value in the F table, but we're also going to need these degrees of freedoms when we calculate our F statistics. So we're going to come back to these in a few minutes. All right, so my challenge here is going to be to try to fit this all on one page. So let's start with our sum of squares within, because that's very easy to calculate. So my sum of squares within, that's just going to be, the formula for that is just sigma sum of squares. So that just means we're going to take the sum of squares from each condition and add them up to get our sum of squares within. So if you go back to that original chart I showed you, the table that had sum of squares in it, you know that for the first condition, the sum of squares was 5.87. For the second condition, it was 1.88. And for the third condition, it was 1.50. So all I'm going to do is add these up to get 9.25. So that's going to be my sum of squares within. My sum of squares between, this one's a little trickier to calculate. The formula for that is sigma t squared divided by n minus g squared divided by big N. All right, so what I have here, remember what sigma means. It means we're going to sum up. So we're going to sum up, we're going to take each t, each total, remember each total within each of our conditions. We're going to square that and divide by n, and then we're going to do our calculations and sum that up. Let me show you what I'm talking about here. So my first t from that table was 29. That was the t for that first condition. 29 squared divided by 8. That's the t squared divided by n there. But I have to do it for each condition. So for my next condition, 13 squared divided by 8. And then for my last condition, 10 squared divided by 8. Okay, so what I've taken, again, for each condition, I've simply taken the t. I'm going to square it, and I'm going to divide by n. My little n, excuse me. And then what I'm going to do is I have to do, that's only the first part of my formula. That's sigma t squared divided by n. I also have to add in the minus g in parentheses squared divided by n. Remember, g was 52. I'm going to square that, divide by 24. So what this is going to give us, when we do our math, it's basically 138.75 minus 112.67. I don't need the brackets there, sorry about that. So 138.75 minus 112.67 is going to give me 26.08. So that's my sum of squared between. My sum of squared within is 9.25. Now, one last thing, if we want to check our work, I'm a big fan of that, is we're going to do, we also want to calculate our sum of squares total. So the formula for that is sigma x squared minus g in parentheses squared divided by big N. Okay, so we've already calculated this g squared divided by big N. We already calculated that with the sum of squares between. So we already have that. Our sigma x squares we also have. I gave that to you earlier. So sigma x squared is 148 minus my g squared is 52 squared divided by 24. And when we calculated that before, we got 112.67. So that's 35.33 for our sum of squares total. Okay, so what we've done here so far, we've calculated 3 different sums of squares. Sums of squares within, which is 9.25, sum of squares between, 26.08, and sum of squares total, which is 35.33. So what I want to do next is I want to put this in a source table so this makes a little more sense to you. And I strongly recommend when you do ANOVA that you make yourself a little source table. It'll help you to keep all the parts straight. ANOVA is not difficult, but it has a lot of moving parts to it, a lot of parts to keep track of. So I think it's good to put this in a table. So our sources of variance, remember what ANOVA is. We're comparing the variance between treatments and the variance within treatments. So we have different sources of variance, and then we also have a total. Okay, so our sum of squared between, which we calculated it already, is 26.08. Our sum of squared within is 9.25. And remember that those should equal our sum of squared total, which is 35.33. So you can check up on me and make sure if you take 26.08 and add 9.25, we should get 35.33. So that's telling me everything's been calculated correctly, since that's all working out. Remember on the previous slide, we calculated degrees of freedom. For between degrees of freedom, it was 2. That's for my numerator. For my denominator within degrees of freedom, it was 21. And our total degrees of freedom was 23. So again, those nicely are adding up nicely. So we know that we've calculated things properly. Okay, so the next thing we need to do, ANOVA is a ratio of variance between treatments and variance within treatments. So remember what you know about variance. To calculate variance, we take sum of squares and we divide by degrees of freedom, right? So that's what the mean squared is. The mean squared is just a fancy name for variance. So what we're going to do for our mean squared between, to get that, we're just going to take the between treatments sum of squares divided by the between treatment degrees of freedom. In other words, we're going to take 26.08 divided by 2, and that's going to give me 13.042. That's going to be the top half of my F ratio. We're going to do the same thing for our sum of squares within treatments. Our sum of squares within treatments, we're going to take that and then divide by our degrees of freedom within treatments to get our mean squared within. So to do that, we take 9.25, divide by 21, and we're going to get 0.440. Okay, so what we're then going to do is we're going to take our mean squared between divided by our mean squared within to get F. So again, F is just a ratio of variance between treatments and variance within treatments. Our mean squared is just that. We've just calculated the variance between treatments and the variance within. Now we just need to divide them. So we're going to take 13.042 divided by 0.440, and that's going to give me 29.61. So this is going to be my F observed. This is my F statistic. This is what we've been working on calculating, 29.61. And if you recall, when we looked up our critical value here, now the F distribution looks a little different. It looks maybe something like this. So if our critical value here was 3.47, this is my critical value. Anything in this shaded area is where we would reject our null hypotheses. Okay, so my F is way out here, so that means I can reject my null. Because my F of 29.61 is bigger than my critical value of 3.47, that means I can reject my null hypotheses. Okay, so what I've shown you here is I've shown you how to calculate sum of squares within, sum of squares between, and sum of squares total. And then I've also shown you how to put that in a source table. This source table is where all the good stuff is. It sort of helps us to organize everything. And what I'm going to do next is I'm going to show you the same data and how it's presented to you in SPSS. In this section, I'm going to show you what the data would look like in SPSS if we were to put it into SPSS, and this is our output. So this is the same data we used before. Remember, our dependent variable is mood. I put that in blue to just remind you what our dependent variable is. Remember, we had 3 conditions, pop, rap, and country. We had means for each of those, so those are presented in the descriptives. You can also see standard deviations and all other descriptive statistics like confidence intervals. What I want you to look at, though, is at the bottom where it says ANOVA, and you see it's a source table. It looks pretty close, although a lot neater, than the one that I did by hand. So if you look, you can see that we have sum of scores between groups or treatments, sum of scores within groups, and sum of scores total. And those reflect very, very closely to the ones we hand calculated. You can see the degrees of freedom are also there. The mean score is calculated, and the F. And you can see that F is very close. That we calculated 29.61. This F is 29.608. So if you round, we basically got the exact same number. If you remember how to report this, remember we report for in manuscripts, we report in papers, in the way I have listed at the bottom of the page, where F, and then we put our degrees of freedom in parentheses, 2 and 21, equals 29.61, and P is less than 0.001. Remember, if that significance level is less than 0.05, we call our results statistically significant. So we have statistically significant results because P is actually less than 0.001. P is very close to 0. Remember what this is telling us. That significance level, it's telling you the likelihood of incorrectly rejecting the null hypotheses, of making a mistake in rejecting the null. That is such a minusculely low number. It's basically 0 here, that we are going to reject our null hypotheses and feel pretty good about it. We're going to reject our null and feel fairly safe that we're not rejecting our null incorrectly. And remember, rejecting the null means that we're saying that the results of our research are because of our independent variable, in this case, the kind of music people were listening to, that it's not due to sampling error. Okay, and one last slide I want to show you. This has to do with, if you remember, when we talked about the hypotheses for ANOVA, remember the research hypothesis is simply that one of the means differs from the other. So we rejected the null, which means our research hypothesis has been supported. Our research hypothesis is saying that at least one of the means differs from the other. The problem is we don't know which means differ from the other. So if we reject the null hypotheses with an ANOVA, and if we have more than 2 conditions, then we need to do what's called post hoc tests. And post hoc tests are where we're comparing the mean from each condition with the mean from every other condition. So if you look, it's basically comparing, and it gets very repetitive. If you look at the larger table there, you can see that if I compare pop and rap, the mean difference is 2. The asterisk there indicates that it's statistically significant, that that's a real difference. Same if I compare pop and country, you can see that the mean difference there is 2.375. That's statistically significant. You can see the little asterisk there. If I compare rap and pop, you can see that the mean, it's the same, it's just a different direction, the way it's being subtracted than up above. That mean difference is -2, that's statistically significant. Rap and country are not, though. That difference of 0.375 is not statistically significantly different. Now, kind of an easier way to look at this. If that feels a little overwhelming to you, one thing I recommend to students is just look at the subsets. If you go over to the smaller box over in the at the bottom of the screen, you can see that I have country, rap, and pop there. And you can see that country and rap are in the same set of 1. They're in the subset of 1. Pop is in the subset of 2. So the way you can look at this is if things are in different subsets, they are statistically significantly different. So what this tells me is that country and rap do not differ from each other. It doesn't matter if people listen to country or rap, that had no difference in their mood. What seems to matter is pop music, that pop music seemed to improve mood compared to rap music and country music. So the pop music had an effect. It's statistically significantly different. That mean of 3.625, that mean is statistically significantly different compared to the mean for country of 1.25 and compared to the mean of rap of 1.625. Okay, and then country and rap don't differ from each other. So essentially what I'm saying here is with my post hoc tests, the pop music was what was increasing people's moods. The pop music had a positive influence on mood. Country and rap did not. And country and rap did not differ from each other in terms of their effect on mood. Okay, so this is, again, if you do an ANOVA and you reject your null hypotheses, if you have more than 2 conditions that you're comparing, you need to then do post hoc tests. You can do these by hand, or you can do them through getting SPSS output. And again, the big table there is comparing each condition with every other condition. It gets a little redundant, so it can be hard to sort of wade through all of that. So instead, what I'm suggesting is that you look at the subsets. And again, if you have means within the same subset, they do not differ from each other. Means that are in different subsets do statistically significantly differ from each other. So what I've done in this lecture is I've shown you how to do hand calculations for a one-way ANOVA. The important thing I think you need to take away from it is what's in that source table. The parts of the one-way ANOVA that are in that source table are important to understand. And then I also showed you how the output looks in SPSS when we use the exact same numbers. Thank you.